Hi.
Okay, so why don't we get started?
Yeah.
Can we start the intros?
Yep.
And just remember, when someone asks a question here, when someone asks a question in the audience, repeat it so we can hear it. Okay. Broadcast on the recording.
Hi folks, I guess we can get started right now. Hope everyone got some food and some drinks. Sorry I was a little late today. Well, welcome to the New York Revit Users Group meeting this month. Usually James is here helping to kick this off, but I'm one of his VPs, so I'm going to help cover him today. And sorry, do you want to hear me?
This is for the, these are for the Zoom, that's for the internet.
Is that better for everyone? So everyone on the go-to meeting, you click on here. Everyone's in listen-only mode, so if you have any questions, please type it in the questions area, and we're not using the raise hand function. So a little bit about the group here. We're over 700 registered members of Meetup. Actually, when I left the office today, it was about 730. It's growing pretty fast. I guess we were founded in April 2006. Started out what was new in Revit Building 9.1. We've been meeting here for this past year here at Pratt. The space provided for free by Karbanowski at Pratt here, and she's also offering. That's the next slide actually. This group's actually a little bit different from most other groups. We are actually sponsored by 4 resellers here in the New York City area. Imagine it, Microdesk, Microsoft Resources and Consulting for Architects. And AI credits are usually managed by HOK, and webcasts provided by SOM. I don't believe this today's meeting is AI credit. So
Totally could be.
This month's sponsor is CFA Staffing. Please visit the website. They specialize in placing architects and interior designers. I think they have placed over 20,000 people in jobs so far. So please do check them out. They're the sponsor for the food and the drinks. And also here at Pratt University, please do visit them at their Center for Continuing Education. They're actually offering us members of the Revit Users Group here 10% on their courses, but you have to be registered on the Meetup group, and when you register, please use your first and last name, because that's how they'll check the list to see if you are actually a member of the group. And I think, according to James, it's much better to call in and register so they can verify it. I'm not sure if you guys know about the Facebook group that we have. James is actually posting most of our interesting links on here, so please do check it out. And, you know, if you guys could come up for a wish list for future topics, that would be great. Anything you guys want to see, anyone wants to present, this is a users group, so it's not so much just a small select group of people presenting. It's more about the community, so hopefully you guys generate any ideas or want to present, just come up, speak to me. Upcoming meetings. So the next month's meeting in January, we have a meeting set up by Ian Atkins, and he's presenting advanced BIM for modular construction. But after that, in February, March, April, May, we're completely open. So we're open to any ideas if anyone wants to present. And then for tonight's speakers, we have Matt Jezyk and Kron from Autodesk. They were presenting performance-based design with Revit. They actually presented something more in-depth at Autodesk University, so hopefully they'll give you a little bit of a taste of what's going on. So without further ado, I'll give it to Zach. Oh, sorry. Matt.
All right, thanks a lot. Hey everybody, my name is Matt Jezyk. I'm a senior manager at Autodesk. I've worked with a lot of you on Revit over the years. We're here today to talk about some other kind of advanced things that we have kicking around in Autodesk Labs. So Zach and I both have worked on the Revit technology for a number of years, And one thing that we're working on now that's a new technology preview is called Project Vasari. So a couple things that we're going to talk about today have to do with tying parametric modeling with different types of analysis. So different types of sustainable design, either running different types of analysis simulation running locally on your machine or running up in the cloud are areas that we're working on today. So we're going to take a little brief spin through that and then figure out ultimately how we can tie a model that has some level of intelligence into it with early and advanced simulation to basically make better decisions and be informed earlier in the design process. So let's really just, we're going to keep the slides, coming quick and light through this whole thing. It won't be a whole lot of time spent on one particular slide, lots of imagery. And we'll try and plow through this in about an hour and leave time for questions. So just a quick overview of what we're doing with this tool. Basically, it's a slimmed-down version of Revit that is available for free as a technology preview. How many people have heard of this tool? Just show of hands. Okay, so about 3/4 of the audience here. So yeah, we have basically this free technology preview focusing on massing, conceptual modeling, conceptual analysis, and then using this as a test bed to try out some new interesting ideas. And that's what the group that Zach and I work in, we're doing inside of the factory up in Waltham. So just a quick, really quick overview of this. And a lot of this content is things that we talked in detail at Autodesk University about. Let's see if this might not play well with GoToMeeting. Basically, with Project Vasari, and let me know if this doesn't play well here, it looks like it's keeping up. You can start to do some preliminary understanding about the site, look at various ideas of blocking and stacking and fitting programmatic requirements into a design, run it through a various set of design analysis, looking at solar radiation, whole building energy analysis, and then tying that into a parametric model that you can start to control and configure, and start to figure out ultimately how well that particular design is going to perform, and then start to evaluate essentially different options early in the design process, either for new construction or for renovation and retrofit work. So here's kind of just the general vision of what we're doing. A lot of the features that we're talking about are tied into new technology that we're working on inside of Autodesk, specifically related to the cloud and analysis, right? So we're moving away from pure modeling into what else we can do inside of the cloud and tying into other capabilities that don't just run on your local computer. So just kind of a quick overview of what we're doing. A couple things that over the last year, I'm not going to read all of these, but basically there's been a strong resonance in the industry using these kind of tools, streamlining workflows, tying things together, and ultimately trying out as many different ideas as possible early in the process and informing the overall later design from there. Both at the low end and also at the high end, looking at various scripting capabilities, and now looking into visual programming capabilities as well are things that we're interested in, and at a variety of scales, both at the macro urban scale and all the way down at the sort of detailed scale. And ultimately what we're trying to do is take capabilities from a variety of different tools and integrate them into a main design application. So just real quick, started from Revit 2011, slimmed down, focused on 3D modeling. A lot of parametric modeling, so focusing on not just making an overall form, but assemblies of forms that understand how they relate to each other. And ultimately behave as essentially a big rig that you can change one thing and have it propagate through the rest of the design. And operate on that in a variety of different ways with various user interface techniques from there. The idea of integrated analysis, so having things that are happening real time in your computer, you don't have to hire a separate consultant or export to a different tool to use these things. And then looking at more advanced things that used to literally have to run for multiple days at a time now can be run on your desktop in real time. So I'd definitely encourage you to take a look at the new tools that we have. We have some pretty interesting things that we're working on around simulation, around parametric modeling, and ultimately making things usable for a larger audience outside of the Revit sort of ecosystem. So that's just kind of my quick overview here. Basically, we think that the industry is kind of at a cusp on how people are looking at not just conceptual design, but overall modeling. And there's a lot of push towards integrated analysis and ultimately getting to something that's more sort of performative design or performance-based design. And we'll talk a little bit more about that in the future. And lastly, if you haven't seen, we have a larger community site called projectvasari.com. Definitely take a look at that if you haven't seen it already. So with that, that's just kind of a quick overview of things that we talked about there. What I want to do now is hand it over to Zach, and he's going to talk about some of the advanced paneling and sort of fabrication techniques that we can do. So it's combining a massing model with different ways to rationalize that and create buildable pieces of geometry from that. And then I'll come on after Zach's done and talk about some other things. Thanks.
Hi, everybody. This is going to be something a little different. So one of the things I want to talk about is sort of a fairly specific set of operations that you can do in the Vasari and in the Revit environment. And a lot of the things that we've been trying to do specifically with Vasari is sort of change people's perceptions about what's possible with this platform. And in particular, I want to go through different methods of looking at geometry and looking at ways of optimizing geometry. About a year ago, we put together a list of what we're calling the parametric design patterns. It's a concept that we picked up from a guy named Robert Woodbury, who's been working particularly with things like generative components. It's an idea of how you can start taking sort of generic ideas about making associative models, making parametric models, making models that are built around the idea of relationships rather than just going out and trying to make a form from nothing, and boiling them down into a couple of repeatable concepts. And I want to walk through a couple of these concepts, particularly around form making. In Revit, one of the basic ways that you can start taking complex geometry and breaking it down is through segmentation. We've got a set of tools that are particularly made for that: curtain system and divided surface. There's some distinct differences between each of them. The curtain system was something that was created a few years back, particularly around stick-built geometry, or stick-built sort of storefront curtain system. And divided surface, which is sort of a more generic way of spreading or repeating points along a surface and sort of connecting the dots. Railings, which have been misappropriated in all sorts of ways, because by and large, geometry for architecture are very small elements that are repeated many, 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 many times. And the railing tool is one of the tools that can do that. So people end up with all sorts of geometry in their buildings that are called railings that are really not. But at base, what you're trying to do in this sort of discretion of your complex geometry is breaking complex geometry up into individual pieces and making manipulations on them. And this is quite handily dealt with by this divided surface functionality. And ultimately, after you sort of divide up complex geometry into individual pieces, you want to replace those individual points with real geometry, whether that's you're making a paneling system for a wall or you're wanting to make a precast element to go into a piece of bridge geometry. It's about sort of breaking things up into these pieces and replacing them with something real in the end. And lastly, and this is the part that I'm going to want to sort of pursue a little bit more in depth, is this idea of pre-rationalization versus post-rationalization when you have complex geometry. One sort of large bucket of approaches is to say, I've got rational forms and I'm going to mix and match them together to make something that is complex. And then another is to say, I'm going to make a sculptural form and then I'm going to break it down into something that I can actually build. This is just an idea of there are different ways to create the same form that are all going to have very different ways of putting the pieces together. These are all spherical forms, but each one of the pieces that make them up have very, very different implications for buildability and cost and construction. And when getting into this idea of rationalizing complex surfaces into buildable pieces, there's sort of two large buckets of places where you would want to go: triangulation versus planar quadrilaterals. There's different advantages to each. There's an idea generally with planar quadrilaterals that you get a nice square flat piece of material. It's going to be lighter, it's going to be glass, it's going to be more transparent. There are certain efficiencies in using that. There's some less flexible, is generally less flexible breaking up geometry into planar quadrilaterals. So there's some trade-offs in each, and again, I'm going to get into this more in a bit. Just going to run through this stuff. And lastly, before getting into some examples, reporting. There's something that you can do in Revit that is almost completely banal, and it's not even worth talking about in some ways, which is that you can get all your pieces and you can list them out in tables and schedules and filters and views. So you can start analyzing your building geometry into pieces that you can isolate into spreadsheets and other things you can get non-geometrical output from it. But if you use a couple of other tools inside of Vasari and Revit, you can start really beefing up that kind of tabular data or graphical data that you can get out of your model. One thing that I talked about last year at AU, sorry we keep referring back to AU, I'm sorry if you didn't get to go to Las Vegas and get jet lagged and drunk, was this idea of creating components and panels that you can cover your surfaces with that will start telling you information about them. In particular, something that I talked about last year was something that was just looking at deformation, looking at surfaces of forms and saying whether or not you could break it into flat pieces or whether they needed to be sort of more complex curvature. And I'm going to use this panel, and if we have time we can explore actually the construction of this, which is sort of a more beefed up version of this, which is essentially, this is a panel which you can repeat over any kind of geometry, and it can start informing you about what's going on with that geometry. It can start telling you things, not only is it flat, but are the edge lengths similar, are the angular relationships similar, and it's basically using this sort of out-of-the-box functionality called reporting parameters, which, has anybody here used reporting parameters? Anybody? Anybody? A couple of people. This is, a couple of years ago we put in this functionality, which is essentially this awesome little dimensional tool where you can connect 2 points and it just tells you what it is all the time. And you can take that information and you can read it out in schedules, you can use it to drive filters, but basically it's a way for you to label geometry in your model in such a way that it can tell you useful things about it. It doesn't actually tell you something like, it's not like a regular dimension, or it's not like a driving parameter as you use other places in Revit, but it's just something that is giving you feedback. And again, you can take that information and you can drive it back down into, into the data model of your Revit and get information out from it. So, a couple of projects where you could use these. These are sort of theoretical projects that were done in other software applications, but you could have done in the new tools in Revit and Vasari. And I'm very happy to say that there are 2 pachyderms. The Elephant House by Foster's and Partner at the Copenhagen Zoo, and the Hippo House of Schlag Bergman and Partners at the Berlin Zoo. These are 2 reasonably complex pieces of geometry that are executed in, I think one was in GC and the other one was done actually in Digital Project. And we actually have somebody who's probably involved in, maybe, no. Let's see that. Yeah, but he was the project. Yeah, anyway. And they use these 2 different paradigms, I think, for form making. One with the Elephant House was based on using geometric primitives to do form making, and then the other on doing a rationalized system for making forms. I'm going to explore a little bit about what that means. So with working with rational primitives, it's basically how do you accumulate things that have known surface properties, toruses, spheres, cubes, and how do you recombine them to make your forms, a tried and true honored way of making forms. And it comes up with donuts. Homer Simpson and Sir Norman Foster have this in common. They both love donuts. On the left, we have the Apple headquarters in Cupertino, a house in England, and the American Air Force Museum, I believe is what it is, in the UK. They're all sections of toruses, and toruses have this great property, along with that donuts are love, and I like donuts myself. They are made, or can be made, entirely out of planar quadrilaterals, and in many cases they have identical pieces. So on the bottom we can see the use of one of those reporting parameter panels that is basically just telling me that all of those panels are made out of absolutely flat pieces, the blue one on the bottom. And the one on the top is giving length measurements on edges. So you can see that banding basically indicates that for a torus, you have bands where each one of those panels is absolutely identical to its neighbor. And this is basically, again, using this idea of reporting parameters and filters with a curtain panel to start analyzing your geometry and knowing what you're working with. So again, here's the elephant house. Looks fairly complex. But when you break it down, you've got two intersecting toruses where you cut off the top of them and panelize them. So pretty straightforward. And it can be constructed in such a way where you just have four parameters, basically four radiuses, the outer radius and then the inner profile radius that define the entire complex geometry of the entire project. And by manipulating those four parameters, you can get all sorts of variations in the form. And then going back over to the Hippo house, we've got something that's a little bit more complex. It takes a little bit more heavy lifting and a little bit more thinking to get going on this project, but I think it's really pretty interesting to look at. Before getting into this, I just wanted to look at a particular way of making forms. So here we've got different methods to make nearly identical forms. We've got a revolve, we've got intersects, which is basically when you take a form, and we've got a tool for basically like a big egg slicer, just chopping right through it. And then this form that I want to talk about a little bit called the translation surface. And the different properties that these different, almost nearly identical forms have. So here we've got the revolve surface, the egg slicer surface, and the translation surface with looking at deflection and looking at edge length. Sorry for the rainbows. I haven't really come up with a good pseudo color combination yet. But what we're seeing here is, again, the banding with the revolved surface, which is very much like that torus that we were looking at. And then on the left, you've got all same edge length and all planar surfaces with this translation surface. And this kind of surface rationalization with the translation surface is something that people have been using for a long time now in packages like CATIA and in generative components to make complex geometry that's really quite buildable. There's a couple of good papers out there on that. If you're really interested in this, I highly recommend pursuing these papers here, Parametric Strategy for Freeform Glass Structures Using Quadrilateral Linear Facets. Or you can just do a Google search for Jim Glimpf and Hans Schober, and you'll pretty much hit this. But the basic principle is that if you lay out a bunch of parallel profiles and you sweep them together, you can get these surfaces that have these magical qualities of being remarkably similar to each other and flat. And so I'm just going to really run pretty quickly through this. So we've got the Hippo house here, sort of roughed out in Vasari, and what we have here are 5 different versions of coming up with very similar geometries. We've got freeform geometry here on the far right, and this is basically just push-pull points all lofted together. We've got a translation surface, which is that big jumble of spaghetti. We've got a sweep, which is just taking a profile and sweeping it along a path. And we've got 2 different kinds of revolutions, tangent, arc, and splines. And just looking here at the translation surface, we've got that big jumble of spaghetti. And basically, if you take a bunch of profiles and you sweep them all together, and then you chop out the shape that you want from it, you can see that that's the translation surface there, 2 in from the right. And this is basically the way that the sort of the natural panelization happens when you're using the divided surface functionality to cut up that surface, just using, and again, just using different form-making strategies. And then applying this panel that's all tricked out with these reporting parameters, you start to be able to mine your forms for all sorts of information. So here is just looking at surface deformation with these different panels, blue being really, really flat, and yellow and orange being really, really not, or very expensive. Looking at edge length similarity, this is in 2-foot increments. So you've got the banding again in the revolutions, and in translation you've got identical elements. And this goes in both directions, up, down, and left, right. And then finally angle matching, and this is where, if you've got a rhombus like this, how do you find other rhombuses that have the same angles? And again, this is just by putting a bunch of information into your curtain panels. You can then mine your surface for all sorts of information about it. And then you can go back and you can take a look and say, well, what suits my needs for my project better? Do I need something that has identical panels? Do I need something that just needs to be similar to each other? In the end, this project was done as a translation surface. Sort of cheated. I just went and found one that was a good example of translation surfaces and tried to do it in Revit. It's pretty easy. And in looking at these sorts of projects, you just sort of need to know what it is that you're needing from a project. If you use these methods, you end up with ragged edges. You have to deal with Boolean operations, which sometimes can be a bit of a pain in the ass. And there's going to be some amount of surface approximation when you're doing this. And there are aesthetic pluses and minuses. But in general, these are methods that, for people that are doing complex geometry, really makes all the difference in the world for cutting down on costs, increasing things like transparency. And for the most part, people are not doing this sort of work in Revit. But what I want to just demonstrate is that this is entirely possible, and it's actually pretty easy once you get going on it. I just did a blog post on it too, which is just sort of showing the steps for making this sort of surface. I want to do some more posts that actually show the construction of the reporting panels that will start mining your model for data. Why don't we come back to it at the end if we've got time? I want to just make sure that we get through all of our other information and we can see.
25 minutes we've got.
Okay. Should we jump into it now? Yeah. Okay. So what I'm going to do is I'm just going to open up, how do we get out? I'm just going to open up one of these models just to sort of show you how these pieces go together for this particular kind of form-making exercise. Pardon the dead air. So after going through the process of looking through, that one scale translation surface where you've got all these profiles basically swept through each other, I was doing some refinements of it actually on the plane on the way down here. I thought it would be sort of fun to look at. So here I've got that same form that we were looking at. And before even getting into all the fancy work of how you can get the reporting parameters to tell you all sorts of information about these things, one of the things that you can do when you're using the panelizing tools is you can just visually inspect these things. Here I've got a panel that's been made on one of these surfaces, and if I just look at it, I can go in and I can visually inspect and see that in fact I've got this thing that is absolutely flat, and so I can start building up a little bit of trust in this process this way. And if I look at this whole surface, if I just select all the pattern components, using out-of-the-box Revit functionality, you can see if you look at the parameters here, these are all of those parameters that are in that individual panel. And I've selected all of them on the surface, and they're all showing up as the same, so I can start understanding what's going on with the surface. And also, if I just look at how this panel is put together, where is it? There it is. I'm going to edit this guy. There's not a whole lot of information that's put into this guy. It's just a regular quadrilateral panel, and that for each edge, I've added one of these reporting parameters. Its only job in the whole world is to tell me how far it is from here to here every time this is placed in a project. And again, so I've got angular dimensions in there too. And I've got this one little point up here that is driven by its association with a triangle out here. So this guy is basically hosted on the intersection between a line going up from the panel and a plane extending across the panel. And what that tells me is, am I flat? So, or not even just am I flat, but how not flat am I? You can see that point going up and down, and then it has hooked onto it this reporting parameter, which is just driving out all that information so that I can tell how flat my panel is. So again, this is just a tool. This isn't really a panel that has real end geometry, but it's just a way to start analyzing your model. And then there's a lot of other things to get into, but more things about how to make these forms themselves are on my blog, which I'll show you. The address for is buildz.info, buildz.info, if you're interested in this sort of stuff. There's a lot more information on this sort of form making. I think that's enough for now while we switch gears to the next bit.
All right, thanks, Zach. So we talked a lot about in previous presentations around different types of analysis, the sustainable design, different pieces of analysis. Zach is showing how to actually make kind of more intelligent models here that can start to report back information. In this case, really about buildability and cost, some level of understanding about how can I start to divide up surfaces. One thing I want to talk about now is switch gears a little bit more to talk about some of the other work that our group is doing, and a different class that actually we taught at Autodesk University last week. And this is really about using a type of analysis that we've been working on the last few years. That's solar insolation calculations, solar radiation coming in, how much is going to hit a certain surface. That's been around for a number of years that our group has created. But one thing that we've been exploring recently is how to create a feedback loop, basically to drive some information from that analysis back into this type of parametric model and use that instead of manually modifying a parameter, feeding that back in and having the software start to optimize. So you start to tie different systems together to get something happening that's pretty interesting. So same kind of principles we just talked about. In this case, we have kind of an urban context, and basically the example is I'm trying to site a new building, and I'm trying to change things like rotation and the angle of the roof to find essentially an optimal position for photovoltaic panels. And the way that I'm going to do that is not by manually changing something, but by using a new open source project that actually is called Dynamo, and it's by a gentleman named Ian Keogh, who used to work at Borough Happold in New York. Now he's in LA. So he's a local guy. He used to be around here until last year. And we've been collaborating on something recently that is an open source effort. You can go and find it online. Definitely encourage you to take a look at it if you're interested in these kind of visual programming sort of interfaces. So basically what he's created is a way to drive the Revit API without having to program, just by connecting sort of visual nodes together in a way that has been around in the industry for a number of years now. And what we're doing here is basically tying these things together to do a very specific purpose of taking a parametric model that we've already created and tying it to suck some information out of some analysis that we're running, and basically taking information from a CSV file, from an Excel file, munging that data around, tabulating it, and then pushing it back into the model to change a specific value. And then we build in some logic that basically does a really trivial type of optimization just called hill climbing. So it takes the current state, compares it to a new state. If the new state is more than the old state, use that state. Just keep on going up until you hit the maximum. And it could be a local maximum, but you're basically there, and that is an optimal state in this condition. Okay? So these are some things that we're actually exploring in this environment, and basically you can just run this thing through and experiment with it. So we can actually go through that in a little later in this presentation if you'd like, but These are just some things that we're working on that are looking at different ways to tie parametric modeling, very smart models, with different types of analysis together. Okay? So with that, we can probably just open it up for questions. I don't know if you want to go through some of this last part or not. Okay. So yeah. So thanks a lot. Yeah.
Yeah, I mentioned that Dynamo. You said it's an open source visual programming now. Does that work on top of, or does it export in a format, or how does that interface with Revit or?
Yeah. So the question is, this is a new topic. This thing called Dynamo. What it does is it runs essentially a plugin or an add-in on top of Revit or Vasari in the very near future. And what it does is basically lets you start to drop in various nodes, various elements there that represent things that you could manually place in the model, but you're just driving it via this graphical representation instead. So it's in its nascency right now. It's really, really new. It's only about 6 weeks old, 8 weeks old right now, but it's available as an open source project, and you can download it today. We have a link in here. We can bring that up as well. You want to show something?
Yeah, if people are interested in it, we can actually just do a quick demonstration of it. But
yeah, I can run through that live here. Do you have the, there it is. Okay. Any other questions while we're getting that going? Yeah, Mike.
I've heard that there are restrictions on Vasari if you want to be working back and forth with Revit, and that there are file problems or incompatibilities, let's say. If you're working in Vasari, do you have to start there and stay there?
Yeah. So the question is, what are the restrictions? How does Vasari relate to overall Revit? The way that we've designed this and set it up is that this is a cut-down version of Revit. It's file format compatible with Revit 2012, and it operates on RVT files, so project files and family files. So if you create something in Vasari, you can take it into Revit, no problem. It's the same. It speaks natively.
Could I be thinking of an earlier version?
Yeah, there was in the very, very early one. But yeah, I mean that's. The one, we do have restrictions on the other way, so you can open up a file from main Revit, and if it has detailed elements like walls, doors, beams, ducts, pipes, they'll still show up, but you just won't be able to make new ones from that because this is focused on the conceptual bit. Yeah.
You might have also been hearing, there's another sort of cut down Revit project out there, which is a separate project called Spark. Which has more restrictions, or different restrictions, I guess I should say, about moving back and forth between the two. But really, what you're getting in Vasari is the same file. You can open one and the other and move them back and forth. Vasari is going to disallow a certain amount of element creation. If you open up a Revit file in Vasari, it might have walls in it, but you're not going to be able to make new walls, and you're not going to be able to do certain manipulations on walls because walls are sort of part of a detailed element workflow, and Vasari is working in sort of an early stage design process and not working with things like windows and walls. So that might have been where you might have heard that sort of thing because Spark does have a different set of restrictions on it. It's also another awesome project out there. Was there another question?
Any other questions?
Yeah, do you have any plans on Vasari tools back in Revit?
Oh, sure. Yeah, so the question is, are there plans to put the Vasari tools back into Revit? So we've been operating for about a year kind of outside of the main mothership, if you will. And we've created a bunch of new features and functionality in combination with various other colleagues inside of the company. But basically, we're using Vasari as a way to, a test bed to try out some new ideas around analysis, integration, usability, all that kind of stuff. I can't, because we're a publicly held company, I can't comment on future functionality as far as commitment to certain time frames. But there are some things that could show up there in the future. Yeah. I have to be vague. Sorry. Absolutely, yeah. So well, the question is, yeah, if I build something in Vasari, will I be able to import it into Revit and use it? So interestingly enough, all the stuff that Zach showed and all the geometric manipulations that we're doing today, you can do in main Revit as is. In Revit 2012, you can do the exact same stuff. And we've had that functionality. Our teams have built that over the last couple of years in the main product. But the thing is, Revit's kind of a big, sort of complicated beast right now. So it might not be inherently obvious how to actually access some of that stuff. But certainly it's possible to do the same thing. And if you make something here, it will go into regular Revit in the same way. Yeah. Does that answer the question? Yes. Oh yeah. The same kind of shapes, lofts, NURB surfaces, all the things that we were talking about here.
One of the confusions about what you can and can't do in Revit and Vasari might also come down to there are certain tools that are enabled in certain families that are not in the main project environment. And that's true for both Vasari and for Revit. So the massing tools, the curtain panel by pattern tools, and the, what do we call it, the generic model by points?
Yeah, adaptive components.
Adaptive components. Those are all particular family and modeling environments that have particular superpowers for making basically more freeform shapes, more flexible shapes, but it's the same restrictions in both Revit and Vasari.
Yeah, so these types of families that you can make, if you use a template, a lot of the behavior and functionality in Revit comes from which template you use. So if you open up the mass template or one called adaptive component, it won't have the standard extrusion, sweep, revolve, blend ways to make geometry that you might use in a regular, like when you're making a chair or something like that. It gives you kind of a more free-form way to create things. Yeah, it's still in there. So the basic idea, and this actually got introduced in Revit 2010 a few years ago. So you can do a level of direct manipulation, start grabbing vertices and points and move them around. But then you also still have parametric control underneath that. So you can always go back in and start modifying the underlying geometry and start editing the sketches and things like that. So it's just a kind of different sort of way to create and manipulate geometry that actually matches kind of industry standards a little bit more, kind of where things are headed.
Although, so just a question for the room. How many people here have actually ever hit the Create Form button?
Okay, so a few people. So this is hopefully a way to open up. There's some other features that might not have been used in your firms before that aren't necessarily just for making massing kind of studies. As Zach showed, you can use these tools at a variety of scales and different levels of detail. So we've been using them with fairly advanced firms on the type of work that Zach was showing previously. So yeah, so that's to answer the question. This is all same functionality that's in Revit 2012 and 2011 and 2010. So yeah, so it's been around for a couple of years. Exactly. So yeah, so what we have done in Vasari is smooth out some of the user interface. So for example, if I was back in the project environment, let's see, this is Zach's computer, so not mine. So a couple things that you can do, like in this case, I'm in a project file now, and there are some various things you can start to do. Just start double-clicking to edit families, say for example, and the context that you're related to will start to gray out. So various things like that, you can start to kind of more smoothly go in and out of different modes and contexts from there. Any other questions? I can get into the Dynamo things. Oh yeah, what was the question?
I wasn't clear about in the presentation was your intended kind of transition from the conceptual surface to the material thickness grow. Right? At what point would you model a document, and at what point keep the integrity of like a mathematical surface? Is that something that you just kind of run back into the Revit world, or more in Vasari?
Well, ideally, okay. So the question was, at what point do do you go from the conceptual, sort of the mathematical or sort of more abstract way of looking at the project and get into real-world geometry? When do you actually start making thicknesses of things and offsets and that sort of thing? Ideally, you never have to make that decision. You can move back and forth because the underlying form is, in here I'm showing masses, is a form that can move forward into the project environment, and you can start using some of the standard Revit tools to build on top of it. So using those underlying forms, so for the Hippo house, you've got that sort of elongated beam shape. That shape can now go into the project environment. You can start doing walls on it. You can start doing more realistic curtain panels or paneling systems on top of it, and go back into the family environment and make alterations to that shape, reload it, and all of the changes are still going to percolate through because your real geometry is hosted on top of this massing. So you should be able to move back and forth. What's that?
So yeah, so that's the overall workflow for massing, like if you have a large change. But even at the more detailed level, so these tools that Zach showed can actually support, creating stick-built or unitized curtain wall, like at different levels of detail. So we have people that actually take, these panels that Zach was showing, and not just create a single surface, but start thickening them up, adding various pieces of materiality and other aspects that represent, real-world buildable pieces here, but not just at the conceptual level. They would use those for documentation purposes as well, and then hand them off to a fabricator.
Yeah. So, for instance, here I'm not going to reload this one, but if I went in and if I make a new curtain panel, I can go in and I can just do a real quick workflow here, where I'll make something that has a real mullion on it, right? Give it a weird round mullion. I'll create a form from it. So say I've developed a real curtain panel, right? And I'm going to load it back into my family. And then you just sort of have the standard parametric substitution, where right now I've got my measuring panel, which is not real-world geometry. It's flat, and it's just got all this weird reporting parameter stuff on it. But I can go in, and now I can substitute it for the family that I just made, which has real geometry on it. And then it percolates through, and it populates the whole surface with thicknesses and other elements that I would want in an actual building, while it thinks about it for a second.
Then, of course, that same geometry can go, into your regular documentation, and also export that information using the scheduling features or whatever else down to sort of the fabrication level. Nice, Zach.
This is really good for a live demo.
Dead air. It's good. But yeah, it'll come back in a second. So yeah. So what other questions as this is coming back? Yeah.
You had sort of alluded to a surface that was feedback with regard to solar insulation, and so I was actually curious to see that demonstration.
Oh, absolutely, yeah. So the question is, we talked about this kind of feedback loop where we basically take data from a source like an ongoing analytical function, consume it, and then push information back into the model. Yeah, and we'll show that in a second. Have you guys heard about this Dynamo thing? Anybody? It's really cool. I mean, I like Ian. I've worked with Ian Keogh for a number of years professionally. There we go. There's that panel back. But this is a really cool open source, feature that he's working on. So yeah, so here's the same panels that Zach mentioned before. Still representative at this level, and this wouldn't be how you would construct a unitized, panel at all. But you can think about the exact same thing. And we have, there are certainly people that are doing this stuff on real projects today. Okay, any other questions about the curtain wall features? No? Okay. Just going to close out some of this stuff. All right. All right, so this This is the example that we used at Autodesk University a couple weeks ago. Basic idea is you've got an urban context here, and we have a site that we're looking at investigating, and some basic idea about a building, just a sort of overall kind of eggshell massing study. And a couple things that we've built into this model are just a way to configure it to control its length and width and height, but maintain a certain level of volume and square footage. So we've built this family so that it literally just maintains a certain size as it gets squished around, just by using kind of standard parametric behaviors in Vasari and Revit. The main things that we're going to worry about today are dealing with things like rotation. So we're going to look at how to rotate this to optimize for solar orientation, and then also dealing with angle. And the way we're expressing angle here is dealing with essentially two heights, front height and a back height. So there's two, and they're basically set up as a formula so that as you change one, it's going to sort of seesaw and modify the other accordingly. Okay. So as I go back into that project, if I change one of these parameters here, like front height, if I drop that down to 30 feet, then the other side is going to go up to basically maintain the overall volume as a proxy for square footage. Okay. So as I change properties here, you'll start to see them update, and I can do them manually here, or I can do it via a parametric control. When we start talking about the analytical features, I'm going to use a tool called the Solar Radiation, Ecotech Solar Radiation, that is built on top of the Revit API, and it's basically taking some calculations that are really valuable from the Ecotech analysis product that we have, and implementing them on top of the Revit platform and on top of Vasari. Basic idea here is that we are computing across a certain time span the amount of incident solar radiation for our site and for a certain location in the world. Okay, so if we take a look just at kind of the first principle level, these things are geographically aware. Buildings are going to be placed somewhere in the world. This one just has a setup for Boston, and as I wait for the connection out, it's set to here. If I bring this down to the whatever 14th. New York. It's going to ask me, well, you mean west or east? So, I can start to precisely position where we are in this context, and then a bunch of other things happen past that. Let's see, there we are. But the basic thing that we're using for this calculation is just latitude, longitude. So what it's doing now is actually computing, based on this position, how much incident solar radiation there is for a certain time range. And we have this set to be a yearly study. You could set this to be a single this kind of still point in time, and you can start to see this obviously update as I change my time of day. It's going to start updating from there. The calculations will update. Okay, you see that? So basic idea here is that we have these calcs that are happening, and this data is being represented graphically, just showing ultimately how much energy is coming in. But there's a series of analytical points that live underneath this, and you can start to show those as well. Oops.
Yeah, you need to make the graphical use.
Yeah. So just talking about kind of the underlying pieces of this overall connectivity. Okay. Oh, did I go the wrong way? There. Too small. I'll get this right the third time. Okay, so we have sample points that are all being computed across the surface, and then real-time these calculations are happening for this. What we can do is actually not just show this stuff graphically, but export it out to a file. And that's what we'll do here. So we have the ability to export this information out. What I'll do is just set up an automatic export of this. And then let me just change this back to be the full multi-day. Okay. So now I have this data that's not just showing up here, but it's being exported out to disk. So there's a nice little file here, and if I open this up, you can start to just see the same data. And it's just a CSV file. The relevant information that we have are for each sample point, an amount of information, the insulation values for that particular sample point. Okay. And all we're going to do in this Dynamo thing is basically read that file and drive that information back in. So now when we launch Dynamo, basically we have this kind of visual programming language that can run on top of the Revit API and Vasari, and you can add various pieces of data to this that represent portions of your model. I'm not going to go through the whole thing right now, just in the interest of time, but I'll just open up a couple of examples here. And Zach, you might need to show me where the sample files are.
Let's see. Want to just do the full vote?
Yeah, just in the interest of wrapping up. Okay, so here we have basically the node representations of this workflow that we're talking about, or workbench. And what we're basically going to do is say we're going to select a particular piece of Revit geometry, a parametric family, by selecting that here. And all that does is basically tell Dynamo we're going to use this particular family downstream and then push some information into it. So basically, when you wire something up here, all you're doing is saying, okay, take that family that I've selected and interrogate it. So there's a different node that its sole purpose in the world is to interrogate that family and start to show for this particular family, it has certain instance parameters. Let's see, there we go. Such as increment, front height, back height, angle, all that kind of stuff. And what this particular node is doing is digging in and saying, okay, for this, show me the instance parameters that are there in this family. And what we're going to do ultimately is drive information back into that.
And just one of the things that I keep coming back to for this stuff is that just this little node right here and this little node right here have sort of a whole world of other information embedded in it, which is sort of the standard Revit parametric family. Grab it, you put it in there, and you describe all this geometry that it does. That's all sort of packed into those two little pieces. And what we're going to do is we're going to basically try and mine that family for information and responses that are built into it.
Yeah, so if you've ever done any programming, and some architects have, some haven't, it's a way to encapsulate this stuff. You don't have to write code from scratch. You can write like a function or a class that all it does is just take inputs, do some calculations, and put some outputs out. You can think about families in that way here. Okay, so just to kind of keep this short and sweet here, so now we know about this family. What we're going to do is hook up the other side of this equation, which is consuming that analysis results. And what we have is basically a node, which its sole job is to read a text file. So we're going to take that and let's see if we can go back to where we placed the auto.
I don't know where you saved out the file to when you were in here. Where did you go? I don't know where you saved it to.
Well, let's just save a new one. Okay. Now I have this the same CSV file in this location. And all we're doing here is just reading that information in, that same text file that we just looked at. Now we read into here, and we have a separate node that its sole job is to add up all those bits of data that we saw before. So this is basically a computed sum of, for the nodes that we have here on this surface across a time period of day, it's adding up that amount of energy. And the goal here is to keep on changing the model until we have the most amount of energy for that surface for a point in time. By basically changing something like rotation or angle, we're going to step through a set of cases and change the model until ultimately this number doesn't get any bigger. It gets smaller. And that's what the other functions here do, where it basically says, hold on to the biggest value that you have. If it gets smaller, don't let it go anymore. And then we have basically some logic that says increment through a series of steps until you hit a max point. So it's kind of like a for next loop or an if-then statement in the model. Okay, so I won't go into a whole lot of detail about this. Yeah.
Is that process brute force, or is there a real mathematical? Because mini-max problems are a real mathematical world out there, like linear programming and stuff. To find a max, you can actually calculate the point.
Absolutely, yeah. This is to be clear. This is a quick demonstration of Dynamo. This isn't an exercise in looking at different ways to run optimization. This doesn't look at the overall field, look at the domain, and try and find local or global maxima, minima. This is a really simple way to do this. It doesn't look into different types of genetic algorithm or anything else like that. But we leave that as an exercise to the reader. So on top of this program, which is open source, you can start to add other nodes that do implement those things.
You mean there's homework?
Yeah, sure. Take your holiday break, Mike, and start adding other nodes. I highly encourage you to do that. There are other people that are doing the exact same thing.
We got some questions here.
Oh, sure.
Just from the back.
Yeah.
Now, I don't know too much about Passing, but based on what I've been told, there's a lot of data function. And I was wondering if Revit was there itself up to the Passing House.
So the question is about Passive House and data collection. So certainly there are different standards and sort of ideals about how to perform different types of sustainable design and achieve certain levels of credit. Certainly if you're going for any kind of lead points, there are ways to use Revit and Vasari to collect information for lead. Same thing for Passive House. We're not actually specifically implementing anything to support those standards, but obviously we're interested in the way in which they develop and how well the industry starts to adopt them. Yeah.
Yeah, and not to be sort of too coy about our example here, but basically what we're trying to demonstrate is just that there are analysis methods and tools inside of the base program, and there are different people, including ourselves, that are exploring ways of trying to sort of scoop up that data, whatever it might be, and reappropriate it and drive it back into geometry. The solar radiation stuff right now is just sort of like an example of how you can generate data from your environment and from your geometry's interaction with it, and how to pipe that back into smart components. But yeah, there's a whole world out there.
Yeah. Okay, so the question is, if Dynamo is an open source effort, and it kind of looks like other nodal wire diagrams like Grasshopper, is there any relationship from a code? I think that was the question, from a code lineage standpoint. We'd have to ask Ian directly, but I mean, Grasshopper itself is not an open source effort. There are ways to program on top of it, but it is in fact owned by McNeil. So that's not something that we're as Autodesk, we're not trying to do anything there. What we're saying is that this is an open source effort that is interesting and supports that on top of a different platform.
And the wire diagram sort of as a model for how to do visual programming has other precedents too. I mean, clearly clearly Grasshopper is something that a lot of people in this space are using, right? There's that same precedent has been used in sort of the music industry for a while, and there's a bunch of other ways to do it. And one of the reasons they keep showing up is that it's kind of fun. It's kind of nice. You can sort of wire things together, and there's a logic to it. And like you were saying, it's flowcharts. If you can do a flowchart, you can do certain basic programming.
And that's the kind of cool thing about this, is that you can start to, if you can think about things logically and break down to a series of steps, you can start to flow them out and capture that logic. Okay, yeah, last question.
Yeah, if it is truly open source, does it have access or the capability to be wired to whatever other program you can figure out the DLL connection for?
Oh, sure, yeah. So the question is, if this is open source, does it have the capability to be wired into other platforms and things that are exposed and have various DLLs and open APIs? The answer is yes. I mean, so this is built on top of the Revit API is built on a .NET programming sort of environment. So our APIs are exposed in a way that is Microsoft compliant, using this sort of standard way to expose things. So Dynamo uses something on top of that and calls into the Revit API. But if you had other tools that can be accessed from a .NET programming language like C#, you can definitely call them and access that, either on your local computer or up in the cloud with a web service. So there are other efforts that are happening right now that literally are pulling information in from some of our other cloud services. Like we have a conceptual energy analysis feature that runs a whole building energy simulation like DO2 up in the cloud. There's no reason why you couldn't start to pull that information down from a web service, not running even locally, and use that in a similar way to what we're doing here. Okay.
With your optimizer here, can you continue to run the program and almost automatically find the best angle and rotation to maximize it? I mean, will it go that far?
This is a particular. So the question is, could you take this optimizer farther and say, give it multiple things to optimize for, like run through rotation, run through angle, run through position? Certainly, that's a whole field of study. There are people that do a whole PhD on that. That could all be done on top of this type of platform. This particular example doesn't do that. It's just a quick and dirty example of it. So yeah.
So this just analyzes one design solution.
Exactly. So what this does is basically just change rotation. So what we're going to do here is just hook up the output from this incrementer into the family just by connecting it here, and that basically tightens that loop up. So you can see that as I change that, the model updates here. So what it's doing is basically changing rotation just based on the input from this calculation. So it's taking the current state of the model, analyzing that, consuming that, parsing the data, and then feeding it into this loop, and then ultimately changing a value that's just basically an increment value in the family that is tied to rotation. So as you change increment from 1 to 2, it says take 2 times a rotation value like 10. So that takes you to 20 degrees. And then increment again will take you to 30 degrees, and then 40 and 50 and 60. So as we step through, all we're doing is simply changing rotation from one to the other. And as such, because we're trying to climb this hill, it'll keep on rotating. And this is a very constrained model, basically saying, okay, for this urban context, not looking at like a green field where there's nothing else around, but in an urban environment, there might be a solution to this space looking at simple rotation that might not be inherently obvious. So it'll keep on stepping until it finds something from there. So right now we have this basically set up, we're using this as a lab exercise at AU, Autodesk University. So what we basically had a way is, instead of automatically running it, we basically would have people manually toggle this back and forth. So by clicking on this button, it'll just step it through the next part in that space. Let's see. Or should. What am I missing here, Zach?
Is the writing new data?
Yeah. Might be that this path changed. Oh yeah, it's writing into the old. No, that's the right one.
Yeah, that's the right one.
Okay.
Do we mention it's pre-alpha?
Yeah, this is. I was writing the code for this on the plane earlier. Okay. I'm in some kind of weird state.
Yeah, I think something broke.
Cool. Okay, so this is definitely pre-alpha. Let's try that again. All right. So imagine, if you will, that it kept on going from there. Okay, so we're just in the interest of time. We can take questions while this starts back up. You're welcome to stick around, and we'll show it in its pristine state. Or we can just keep on answering questions along the way. Yeah.
That's great.
Yeah, so the question is, does this Dynamo plugin work in Revit as well? It certainly does. So you can download that now, and it'll run on top of Revit.
So it shouldn't matter which opportunity the company, but it's only specific properties, not just doesn't care.
Yeah, it's just looking at the family geometry and consuming it from there. Yeah.
Do you know anyone who's used this for zoning analysis?
The question is, has anyone used this for zoning analysis? Certainly firms are using the conceptual modeling tools for various types of zoning, looking at FAR, looking at blocking and stacking and sort of configuring information, and then building, firms have built API applications that change the logic of how things are oriented based on zoning configurations or based on other criteria. They're not using Dynamo necessarily, but they're using the Revit API to support adding other logic that doesn't necessarily require someone to manually change something.
But does it look like something?
Oh, sure. Yeah, it's all possible.
It's new.
Yeah, I mean Dynamo literally came out, a month and a half ago.
People are definitely using the raw API to do that sort of work. People are not using Dynamo yet to do that sort of work. Dynamo is sort of an expression in a graphical manner of sort of the tip of the iceberg of the tools that are available through the API. But yeah, the API has been available for years in Revit. It just is required that you have somebody on board who knows a thing or two about programming.
So yeah.
Keep going.
Sorry. Oh, that's a great question. Yeah, so
I've got Python on there if you want.
Yeah. So there's a separate effort that is another open source effort called Iron Python for Revit. Which one thing that how many people have programmed in the audience? A few people. Okay, so typically when you write like a real program, you have to go into a separate environment called an IDE, an integrated development environment, and write code and compile it, and it's kind of scary. And then it runs or it doesn't run. And you have to debug it. That's kind of tedious, and a lot of people don't want to get into that. There are other ways to program that are basically a scripting language. It's basically is an easier way to run something that you just write a quick script. You can actually compile it right then and there in a way that can run very quickly in an interpreted manner and get immediate feedback and see if it works or doesn't. And that is something that we can support on top of Revit and Vasari now as well. It used to be that you have to go into a separate environment to program. But now using languages like Python that are very generic, very used across the industry, and more importantly, they've been mapped to the Revit API, you can start to do the exact same thing. And we have an example of that here that'll come up in a second as well. So this environment right here.
So what we were told years ago that you had to leave the whole environment and compile it separately and bring it back in and see if it run. You now have something that works sort of like deviated.
Exactly, yeah. So the question is, so now does this change the sort of prescribed way to develop on top of the Revit API? Well, it used to be that you have to go into a separate environment, like I said. There was something called Visual Studio Tools for Applications that lets you get into a more script-like environment, but you still ultimately need it to compile. This is taking it a little bit further. Sorry for getting a little geeky here. This is a pure interpreted language that runs on top, so you don't need to recompile. You don't need to drop the application and come back. Yeah, you should take a look at this too. This is what our team does, is either develop these things ourselves or work with various other interested parties that are out there that are developing these things because they're advancing the state of, ultimately the Revit platform.
Sorry, this is super geeky, but we can get into this if you want. This is the create components thing.
We're going to show how nerdy we are here.
Right. So this is just to your question about scripting. This is a little script that just goes through and it creates a bunch of points in space. And I can live edit the script that creates those points over here, just in a text editing file. There's a little bit of code at the front that calls some of the information that's important only to the Revit API. And then it's actually doing some stuff that's very generic math to any kind of API. So people who are familiar with how to do this sort of work, we'll be able to sort of more quickly enter into the process of using these tools. I haven't used this script in a while, but basically if I wanted to change how these points were laid out in space, now I can just go in and I can at the times maybe do this correctly if I can remember. And I just save it, and then I can just rerun it. And one of the things, so here's my altered script and the original script. So basically just, you don't have to go and you don't have to do a fully compiled application and then write a plugin and then plug your plugin and you can just start interacting.
So yeah, so that's kind of where we are with some of the tools that either our group inside of Autodesk is developing or working with other people outside in the industry that are either developing things as open source efforts or other initiatives. Definitely welcome to stick around, and we can rerun the Dynamo thing if you'd like. But if you'd like to depart, please feel free. Yeah. This is just a text editor called Crimson Editor.
But the project itself is it's called Revit Python Shell, and it's done. It's created by a guy named Darren Thomas. He works out at the ETH in Switzerland. And it's another open source project. He's letting people contribute it or just do whatever they want with it. So.
Okay. So do you guys want to see it? Let's try this Dynamo thing again. All right. Okay. So as I mentioned before, so we have this parametric family. We're going to start up the Dynamo sort of project here, and then we're going to just load this workbench that has a pre-configured set of things here. Select that instance. We're going to interrogate it. And then do the solar radiation calculation. One last time. This will take just a second. Okay. And then we're just going to read that file in. We get this data. And now we're just going to wire it into the family. Okay, so now we see it update. And then as we toggle this, there we go. So now it works. Okay, great. So as I step through this, you can start to see that rotation value is changing. And what we're doing is just stepping through to find an optimal shape. And the way we can tell that is if you read the numbers that are coming out of the computed sum and the optimizer, the computed sum value is going to maintain, it's going to keep on getting bigger along the way. Some other little bug is happening here. So it'll keep on stepping around until it gets to the optimal shape. There we go. So it'll just keep on going, and I think the magic number is around 13. And the logic that's hitting is basically saying keep on stepping until you hit either hit the max number of iterations or hit a max value. So you can see we're at increment number 8 right now, and I think it'll probably end up going to around 13 or so as we step through. And of course, you can fully automate this as well as just a teaching tool for the class that we taught. And then as we hit that max value, it'll stop. That's basically what it's doing. It's climbing a uphill where these values are getting bigger. The proxy of this is the amount of yellow. This just means that there's more and more energy coming in. So it'll keep on going until it doesn't. And when it doesn't, that is essentially the local optimum. And that's kind of where we are right now. So it hit 13 iterations, and you can see that the computed sum is actually larger or smaller than the optimal that's here now. So we're at a local optimum right now. Okay? So that is basically using Dynamo and a lot of the analytical tools that we have to create a really, really preliminary optimization loop on top of Project Vasari. So thanks a lot. All right. So should I stop the recording questions? Okay.
Well, that's the end of the meeting, and thanks for everyone for coming in. See you guys next month. Bye.
We totally forgot. What else?